just need to aware that your system is not symmetric, so you need to recalculate the things. This is the system within yes, right? So now you're gonna do it the other way around. So you have this one, right? And there's a moment, the force, and also a moment acting like this. So basically, you just integrate it, but right now your system we used to do it this way, right? So your fixed support is sticking to the big end. Now your fixed support is sticking to the smaller end. Okay, so you integrate it again, but just make sure that your direction is correct, and then the function that describes this shape is correct. Right? Now your what is it? The curvature diagram will be different because the cross section, okay, variation is different. Okay, so if you have the P acting like this, your curvature diagram will be reversed from the other case. Alright, so you can actually, I don't think it take you so much time to finish this homework, right? It's not that long. You still have a weekend, right? Long holiday, weekend, Mother's Day, go to Future Park, wherever. I'm pretty sure because it doesn't really take much time. So, we may not need to finish it up, okay? It is the matter of fact that you just play around with the, it's not too long. So just play around with mathematical functions, integration, etc., etc. Okay, and then you end up with the stiffness matrix of this thing. Okay, right? If you can do half of it, then the other half of it you'll be able to do. Right? So now we derive stiffness matrix of the bar, of the beam, non-prismatic bar, non-prismatic beam, maybe the EI uniform in some segment, and then an abrupt change of the EI or EA, okay? Those kind of things you can do now. The next thing I want to drag you through, okay? Because we're gonna need these components for your structural analysis of for the direct stiffness method. Okay, so force vector. Force vector, basically the system that we are working on, okay, well, we are coming back to this thing later, but we have the system, alright, stiffness to the u, okay, the vector of displacement, okay, and then you end up with the other side, which is the force, alright. Force will be the vector, u will be the vector, k is the matrix, okay. The thing is that the force, okay, vector over here, it is a nodal force, okay, it belongs to the nodal point. Okay, right. That means this calculation will be possible if you have nodal point force, right? But in reality, you don't really have just nodal point force, all right, acting. Okay, for example, in your beam, okay, which is very general, that okay, you might have degree of freedom here, there, and there, all right. But you have a force distribution like this, and then moment is distributed over the beam, for example. Okay, so the thing is not belong to individual point particularly. It's not just like a point load acting or moment load acting at the node. Okay, this does not just belong to one node. This has effects to many nodes. Okay, it's like sort of distributed force going on or even for the trust member. Okay, for example, well, the thing that you think is the easiest one, trust member, if you don't apply the load like this to the nodal point, okay, well, you might have something that is sort of like distributed force, okay, along the member. Okay, how you come up with the nodal point force. So this is the issue, all right, that we will try to find this out, okay. And so why don't we just start from the easiest thing first, all right, the bar element. In order to find the equivalent nodal point force, okay, for any kinds of load, okay, maybe we start Thursday morning with easiest thing like this. Let's make it F, the little f being the distributed load over the length, okay, so F is the intensity. Well, let's make it f of x is equal to just f like this. So it is just the uniformly distributed line load over your bar element. Okay, so start with a simple one. You have the EA constant, the length of the bar is equals to L, okay, just like we have seen before. So now we want to know, okay, what is this uniformly distributed line load equivalent to, okay, in terms of nodal point force, okay? Because you cannot put this into this system of equation. We formulate our equation based on the nodal point, okay? So that's how equation is formed. All right, so how to do? Just pretty much the same idea as before, okay? So we try to find the corresponding forces that is required to keep these two nodes stationary, all right? It is a little different from before. Before we find corresponding forces that is required to deform your structure at one DOF at a time. But for this one, now the load is the load, not the deformation load like before, okay? If you think of deformation as a load, well, your structure, when it is deformed, you have the corresponding reactions. Likewise, now you apply the load on your structure, then you have something on the supports also. All right, so, okay. But the thing is that now we are talking about the bar element. Bar element, you are considering just the equilibrium along the x-axis. Along the x-axis, you have sigma f x equals to 0. Okay, just one equation. Then that's not sufficient for you to calculate reactions that makes two unknowns, right? Okay, you have two unknowns over here, so you have here and there two reactions. Two unknowns, one equation, not enough, right? So you just release one node temporarily, okay? So this is the technique you're familiar with in your undergrad level and something that we have done over here also. Okay, so let's temporarily release this node, okay? And then I apply this thing. Okay, all right? This is the first system. Add up with another system that you have the force applied like so, okay? So I call this one F2, all right? What should be the nice notation? Let's just make it P, okay? Make it F2, then it will be confusing. Okay, P. And then this one is your R, okay? Alright? To determine the R, okay, when we talk about the arrow design things in your homework as I graded, sometimes you have sort of thing like, okay, this is equal to 6 EI over L squared, for example. So I'm not so sure what do you mean between this actually is equivalent to this one